So formal charge is kind of this math trick that we came out with to help us figure out when we draw a picture, if it's the picture that really should be what we're getting when we look at it with our different instrumentation. So it affects things in kind of two situations. And then I'm going to jump to this one first. If there's multiple structures that can be drawn for an atom, you'll notice that down here at the bottom, we actually drew this in our chart too. There was a CO2. And I kept saying, okay, this could be a possibility, and we're going to rule it out. So that's what we're going to be ruling out. But you also could try throwing the oxygen in the middle of it. So when there's possibilities, like you could draw it in a few different ways. Formal charge is a way to make sure that we get the structure that will be what the structure really is, like what it comes out to when you look at it with instruments. The other one is when the central atom is when it's the third row or lower and the oxygen's on the outside. So if you remember way up here, we were talking about how these ones right here, those have to have 8, but the ones below it can't expand their octets. So these expanding octet ones, when they have something like oxygen, or sometimes sulfur too, but especially oxygen, when they have them on the outside and it's one of these elements in here, sometimes formal charges change something about it. So kind of be aware those are the two cases that we're thinking through, and we'll show some examples with. So how do you do formal charge, and what is it really? Well, all right. It's the charge of an atom. It's the hypothetical charge that an atom has if we would redistribute the electrons in the bonds evenly between the atoms. It's not the actual charge of the atom in the molecule. It's bookkeeping. It's not really a real thing. It's just this little math trick we've worked out. So what you want to do on a structure is you want to figure out the formal charge per atom. So you want this one's formal charge, this one's, and this one's. And we use this little equation. Now we can get that equation simpler, and after we do a round of it, I'll show you how it gets simpler, and an even simpler way than the second way. So I've got 3 ways to do it. So let's start by looking at this chlorine right here. So chlorine, and then we're also going to look at boron. So I'll do them kind of at the same time. So the formula is that the formal charge is the valence electrons. So for chlorine, that's 7. Boron, that's 3. You can go back and look at valence if you're not sure. Minus lone pair electrons. And that's all of the lone pair electrons. So I'm just going to put LP. So chlorine here has 1, 2, 3, 4, 5, 6 lone pairs. Minus all the bonding electrons. But it's half. You do half times all the bonding electrons. So there's a total of 1, 2 in there. So that gives us 7 minus 6 minus 1, which gives us that the formal charge is 0. That's good. Best case scenario, everything has a formal charge of 0. So 0 means good for formal charges. Let's look at this boron right here. So that boron, it's 3. Now notice he doesn't have any lone pairs on him. So minus 0 lone pairs, minus, and then it's half, again, of the bonding electrons. So 1, 2, 3, 4, 5, 6. So this tells us that we're 3 minus 0 minus 3, which gives us 0. Again, that's great. Now, you should really do it for all of the atoms, but there's a shortcut. One shortcut is that when the atom looks exactly the same, so you can tell this chlorine, it's got like the same number of bonds, they have the same number of bonds, and they got the same number of lone pairs. You're going to get the same formal charge for the atoms that all have the same bonds and the same lone pairs. So this is actually the formal charge for all the chlorines, not just one of them. We're going to do this with the equation again. Make sure you've got practice with that before we shorten it just a little bit. So this is oxygen. The valence electrons are 6 minus, and then we've got our lone pair, and this is all of the lone pairs. So that's 4. 1, 2, 3, 4, minus half, and then this is our bonding. So we have 1, 2, 3, 4 that are bonding. So it's 6 minus 4 minus 2 gives us 0. Hey, that's great. Oxygen is 0. Notice that the hydrogens are actually the same. And here's a little hint. You rarely have to do formal charge for hydrogen because hydrogens don't have lone pairs and they all only have one bond. So hydrogen's valence is 1 minus 1, and I should say 1 minus 0 lone pairs minus 1 half times 2 bonding electrons gives us 1 minus 0 minus 1, which gives us 0. And I would expect all the hydrogens that you deal with to be 0. So this is how we do formal charge. Notice all these came out with 0, and that was intentional. Let's make the formula slightly easier. You could also call it valence minus dots minus lines. So let's do that one for chlorine. So chlorine has 7 valence. He's got 1, 2, 3, 4, 5, 6 dots, and he's got 1 line. Okay, that works. Boron, 3 minus 0 dots minus 1, 2, 3 lines. That gives us 0. So over here, oxygen, valence minus dots minus lines. 6 minus 1, 2, 3, 4 dots minus 1, 2 lines. So if you don't have to deal with 1/2, you can just count the line as a full number. Is there an even faster way? Yeah, there is a faster way, but I call this the Megan method. And if you don't get it or you don't like it, then don't use it, just use one of the other ones. I just know that this rings with some people, it just rings with them. So that's why I do mention it. So if you go back into one of these, sometimes it's nice not to write down any math at all. So what I'm doing is I'm placing my pencil on the boron. So do you see I made that mark? My pencil is sitting on it. While he's sitting on the boron, I say his valence count, 3. And then I touch something, and every time on the sides, I take off 1. So this is 3, 2, 1, 0. So my boron's formal charge is 0. Let me do it for chlorine. So again, I state the valence by touching the central atom. So 7, every time I touch something, I take away. 6, 5, 4, 3, 2, 1, 0. My chlorine is 0. I'll do it over here. So my oxygen, he's 6, 5, 4, 3, 2, 1, 0. And then my hydrogen, 1 minus 1 is 0. So if that doesn't work for you, or you don't get it consistently the whole time, then don't use that method. It's just something that works for some people. A lot of people prefer the dots and lines, and that works too. So here's the rules behind the formal charges. All zeros is best. That's your goal. That's what you want it to happen. It doesn't always happen. Second step, if you have all of them being non-zeros, the lowest number of a +1 or a -1 is much better than having 2s or 3s. So for example, we have all zeros here, so that's the first rule. So that means this is the correct structure. But if we were trying to find the next best structure, the second rule helps us with that. And so the next best structure would be this one, because it has 1s and -1s versus 2s and -2s. This one's a really bad structure. Third, if this is the same and this is the same, then adjacent formal charges should be positive and negative, making a 0. So I don't have an example here that really shows this, but it means, again, we've already picked this as the best structure, but it likes it when a positive and a negative charge, it likes it when they're beside each other. And then the other thing is, if you are stuck with a negative, that the negative formal charge, it should be on the more electronegative atom. And if you don't remember that trend from the other chapter, we will be getting to it right after this section. So make sure and look through these, compare these in your head, and we're going to scroll on down to the chart so we can practice on the chart.